Okay, so we're going to start into chapter 15 now. Chapter 15 is going to be really short. We're just going to cover a few things. And then we'll start into chapter 16. Okay. So we're just going to talk about solubility a little bit. And last semester in Chem 1, you probably used one of these charts that allowed you to predict the precipitation of a reaction between two ions, okay, whether they would precipitate or not, whether it was soluble or insoluble. Insoluble products would precipitate, soluble ones would not. And so we're going to look at that in a little more depth, because in reality, everything is soluble to a certain point. And so if you have it in the right concentrations, it will be dissolved until you bring it to a saturated concentration where it precipitates. So some of it will remain dissolved, the rest of it will precipitate. And so that's what we're going to talk about, solubility equilibria. Okay? And we're going to be able to calculate and predict the solubility and the equilibria of these molecules. So here we have an example of silver and chlorine. So last semester you had a chart and it said chlorine is soluble with 3 exceptions: silver, mercury, and lead. So if you add silver to chlorine to silver, mercury, or lead, it will become an insoluble precipitate. Okay? So that's what we see here. This is the equilibria of it. Silver dissociates into silver chloride dissociates into silver and chlorine. Okay, so silver is a solid here. Silver chloride, excuse me. Silver chloride is the solid. Silver and chlorine are aqueous, and they are therefore dissolved in equilibria with silver chloride. So if I was going to write the equilibrium constant equation for this, okay, you're already laughing.
Another K.
Another K, okay, which is just a K. It's just an equilibrium constant. Kc, Ka, Kb, they're all equilibrium constants, right? The Kw. But what do we notice about this one? Well, this silver chloride is solid, right? So do we include it? No, it's not included. So really, the Ksp here, the equilibrium solubility constant, is simply equal to the concentration of silver times the concentration of chlorine. Okay? And the concentration of silver and chlorine, they're going to be the same, because silver chloride will dissociate into equal parts. Okay? So we could simplify this. Let me see if they do. If they don't, then I will. Okay? We could simplify the Ksp here to be Ksp equals S squared. And we're going to use S instead of X as the solubility concentration. Okay? Because here we could say this is S and this is S, because they're both at the exact same concentration. So we could simplify it into being that the Ksp is equal to S squared for silver chloride. So this is probably the simplest example that you would see. Okay, here we see magnesium fluoride dissociates into 1 magnesium and 2 fluorines. So here this is going to complicate it slightly, because when I set up my Ksp, I have 1 magnesium and I have a fluorine squared. Okay? Here for silver carbonate, all right, I have 2 silvers, so that's silver squared and 1 carbonate. Here I have calcium phosphate. Okay, I have 3 calciums and 2 phosphates. So Ca3, PO4, 3 minus squared. Okay? All right. Now, how do I know when this equilibria is saturated, unsaturated, or supersaturated? Okay? So if my Q, remember Q? Q is the reaction quotient, and it determines which way it's going. Okay? So if Q, the initial concentrations, if I calculate Q from the initial concentrations, and it is less than my KSP, then that means my solution is unsaturated, and it will continue to dissolve. So if I put some salt, sodium chloride, into water, and it dissolves, and it all goes away, that means Q is less than its KSP, and therefore it is not saturated yet. It is unsaturated, and so it's all dissolving. So I get no precipitate. Now if Q is equal to KSP, then that's when my solution has become saturated. This is a saturated solution, okay, and it is at equilibrium. If my Q is greater than my KSP, then that is a supersaturated solution. What happens if you have a supersaturated solution? Then you'll get a precipitate. Okay? The precipitate will form and come out of solution. So it all has to do with this equilibria that we're talking about, whether these precipitates form or not. So in the laboratory, when we put two things together and we say they're insoluble and they come out of solution, that's because their Q was greater than their KSP, and so it was a supersaturated solution, and so it precipitated. Does that mean that none of it remained in solution? No, there's still some in solution. It's just that everything extra came out as a precipitate. Okay? Okay, so here are the KSPs for a bunch of stuff. Okay? You can see that some of these KSPs are very small, like copper hydroxide, 2.2 times 10 to the negative 20. So for copper hydroxide, we would assume that you would form a precipitate very easily. If you had copper and hydroxide in even small quantities, they would precipitate out. Or look at copper sulfide, 6 times 10 to the negative 37. Okay, so this guy is not very soluble at all. Hardly any of it would be in solution. Okay? So things that would be more soluble would be things like lead chloride. Oh, look at this guy. Bismuth sulfide, 1.6 times 10 to the negative 72. Okay? So that's kind of how these KSPs they're telling us kind of the solubility of these things. Okay, what's more soluble, what's less soluble at certain concentrations. Okay? So the molar solubility is described as the number of moles of solute dissolved in 1 liter. So we can describe it in molar solubilities or in even gram solubilities. Okay? So, but this is how we are describing it here with the solubility constants that we're using. Okay, so we can also have gram per liter is the number of grams of solute dissolved in a liter. Okay? So the solubility of a compound is to its molar solubility, to the concentration of cations, to the KSP of the compound. Okay? From the KSP of the compound, we would determine the concentration of the cations and anions, and that would describe its molar solubility and the solubility of the compound itself. Okay? So we'll walk through some of these steps. So what is the solubility of silver chloride in grams per liter. Okay, so we want to find its solubility in grams per liter. So, and silver chloride we described earlier, we showed that the KSP for that to be equal to the concentration of silver and the concentration of chlorine. Okay, whoops. So initially, just like we would normally, we'd say the silver and the chlorine are at 0. The silver chloride is the thing that we would start with. Do we care how much we start with?
No.
Why not? It's a solid. It doesn't matter. It doesn't matter what well, it doesn't have a concentration. It's a solid thing, so it can't go into this equation, right? So whenever we have a liquid or a solid, do we put anything here? No, we don't. Okay? So like I said, we're going to use S instead of X for solubility. So here we're going to say plus X plus, or plus S, and so at equilibrium we'll have S and S. And so our KSP is then equal to S squared, which is silver times chlorine, S squared. Okay? So S is simply equal to the square root of the KSP. So this is the simplest example of how you would find S, okay? You would take the square root of the KSP. So S here is 1.3 times 10 to the negative 5. Okay, so that is the solubility, okay? So silver, the concentration of silver is equal to 1.3 times 10 to the negative 5 molar. The concentration of chlorine is equal to 1.3 times 10 to the negative 5 molar. Okay, and we're just by putting in our, for S here in our equilibrium, our Rice table, okay, we get those. So the solubility of silver chloride would be equal to 1.3 times 10 negative 5 moles per liter. So this is molar solubility. So when we say it's the molar, right, the molarity is the molar solubility here. But we don't want it, that's not our answer, right, because we don't want it in molar solubility. We want it in the grams per liter solubility. So we just do one simple conversion from the moles to the grams. The moles cancel.
So your S equals the molar solubility of the solid?
Yes.
Okay.
It equals the molar solubility of silver chloride. Yes.
So you don't have to square the 1.3 times 10 to the negative 5 since it's for Ag and Ca?
No. You don't. The molar solubility is described by the concentration of these things in solution.
So what happens if one of them was a 2 or something? Which one would you use?
What do you mean?
Like if it was Ag2Cl into...
You use it, you solve for S. Whatever
So
S,
just the base
what
S.
S is,
Okay.
you solve for S, and that is your solubility.
Okay.
Okay? You solve for S, that's what you will describe the solubility. Okay? So if there is a 2 in there, you have to square it to, you have to consider that when you solve for S here, and you'll find it. Okay? Okay, come on. Okay, so here are a few KSP expressions. So like we said for silver chloride, very simple. The cation is S, the anion is S. The KSP is equal to S squared. Okay. Same thing here for barium sulfate. But for silver carbonate, it changes because we have a silver squared, Ag2, right? Well, when we describe the cation, it's 2S. So if I was doing a Rice table for silver carbonate, Ag2, okay, dissociates into 2Ag plus CO3 2 minus. Okay. This is at 0. This is at 0. Okay. What is this?
2S.
Plus 2. Come on. Plus 2s, and this is just s, right? So when I write my KSP for that, it is equal to what?
4S.
Well, it's going to be equal to 2s squared times s. Okay? So that's how they're getting here. So if I combine all this, 2s squared is what?
4S.
Okay? 4s squared times s equals 4s cubed. So they simplified it into 4s cubed. That's how they get to here. KSP is equal to 4s cubed, and then from your KSP, you can solve for s. And s is the solubility, okay? The molar solubility. All right, so that's how they're getting all these KSP expressions here, okay? So if it is, same thing here, if one of them is 2s, you're going to get 4s cubed. If one of them is 3s, then it's going to come out to 27s to the power 4. Okay? And here, even more complicated. Okay?
Why is it to the third?
Up there?
It's cubed. Yeah.
Because if I get 4s squared, 4 times s squared times s squared times s is what? If I have an s squared times another s, and I multiply those two, that gives me s cubed. You okay with that? Yeah. Okay. So I get 4s cubed in the end. Okay. Now you're not really going to see a lot of this kind of stuff. Okay. More this and maybe these situations here. Okay. Okay, if 2 milliliters of 0.2 molar sodium hydroxide are added to 1 liter of 0.1 molar calcium chloride, will a precipitate form? How are we going to know if a precipitate forms or not? We have to find Q. And they'll give us a KSP, right? Because there's a big old chart of KSPs, and we can find the KSP for this, and it will describe whether a precipitate forms or not. But we have to know the correct equilibrium expression, the correct KSP expression to be able to solve for Q. So is Q greater than KSP for calcium hydroxide? Okay. So calcium 2 plus equals 0.1. Hydroxide equals 4 times 10 to the negative 4 molar. How did we get all that?
So how do you know calcium? So how do you know Cl is so Cl and Na are just the spectator bones? Chlorine,
Yes.
sodium.
Sodium has nothing to do with this, because we're looking for because if we look at the solubility precipitation rules, okay, sodium and chlorine, sodium chloride will not
Oh, it'll stay. It'll go away.
create a precipitate, okay? But calcium hydroxide will.
Insoluble.
It's insoluble, okay? Hydroxides are insoluble unless they're with one of the metals of the first column of the periodic table. If they're with an alkaline earth metal, though, they will be insoluble precipitates. But did we add enough to make it precipitate? Okay? So where did I get these numbers of calcium 2 plus equals 0.1 molar and hydroxide equals 4.0 times 10 to the negative 4 molar?
Is it M1 times 2?
Yeah, I gotta calculate the dilutions, right? Because if I add 2 milliliters of 0.2 molar sodium hydroxide to 1 liter of 0.1 molar calcium chloride, okay, the 0.1 molar calcium chloride isn't really going to change volume very much. So that's why it just ends up being 0.1, because it rounds back to that. Because it'll be, basically you change the volume to 1.002 liters, okay, which isn't going to significantly change it. But the 2 milliliters, that's a very tiny amount, and you diluted that into 1,000 milliliters. So you have 1,002 milliliters, okay, 1,002 milliliters. If you do M1V1 equals M2V2, then hydroxide, the concentration of the hydroxide comes out to be 4 times 10 to the negative 4 molar. Okay? So that's where we get these concentrations, these initial concentrations from. So I have my initial concentrations. I want to know if Q is greater than my KSP. Okay? So this is what I get for Q. Q equals calcium 2 plus times OH minus squared. Okay, because this is going to dissociate into 1 calcium, 2 plus 2 OH minuses. Right? Okay, so this will equal my Q. So I can calculate Q now. Q 0.1 times 4 times 10 to the negative 4 squared equals 1.6 times 10 to the negative 8. So now I need to compare that to my KSP. The KSP for calcium hydroxide is 8 times 10 to the negative 6. Okay? So Q is less than my KSP, so no precipitate will form. So that's what I'm going to use these KSPs and Qs for, to determine if a precipitate is going to form or not. So once again, this is just equilibrium calculations. We're just looking at concentrations. We're comparing Qs to KSPs. Okay, and that's allowing us to decide something. It's allowing us to determine whether precipitates will form or not. So because Q is less than the KSP, it won't form. How would it have formed? Well, if Q was greater than the KSP, then a precipitate would have formed. Then it would have been super saturated and it would have precipitated out of solution. Okay? Until it had reached its equilibrium again. It would have got rid of all that extra until it reached its equilibrium.
Here the KSP was given, right? It was already given, right?
Yes, it's given to you. Right, we didn't have to do anything to find that. The KSP is given to us from, it would be in the question or from a chart. You would get it from a table. The KSP for calcium hydroxide. Okay. Okay, so let's try another one. What concentration of silver is required? So this is going to be a little different of a question. The other one was pretty straightforward. That was kind of the simplest situation. This one's a little more complicated. What concentration of silver is required to precipitate only silver bromide in a solution that contains both bromine and chlorine at a concentration of 0.02 molar? Okay, so silver bromide must be less soluble than silver chloride, right? Because if we're going to, what concentration of silver is required to precipitate only silver bromide? So by knowing the KSPs, we would be able to determine the solubilities of silver chloride and silver bromide. Okay, so here's the KSP for silver bromide, 7.7 times 10 to the negative 13. Okay, so if I want to know the concentration of silver that's going to precipitate, I guess the least amount of silver, what concentration of silver will allow me to precipitate it. Okay, well that's what my KSP is equal to, silver and bromine here. Okay, so 7.7 times 10 negative 3, negative 13 is my KSP divided by the concentration of bromine, which is 0.02 molar, and I get 3.9 times 10 negative 11 molar silver. Okay, this would allow me to precipitate the bromine. Here's the KSP for silver chloride, 1.6 times 10 negative 10. You do the same thing. Okay, silver, it's KSP divided by the concentration of the chlorine, 8 times 10 negative 9 molar. So we have these two molarities. Okay, so at silver at a concentration of 3.9 times 10 negative 11 molar will be at equilibrium with the bromine. If I go above that, it's going to precipitate. Okay, but if I don't want to precipitate any silver chloride, then I cannot reach a silver concentration of 8 times 10 to the negative 9. So that's kind of the range of where I would have to, of the concentration of silver that I would have to add to essentially create silver bromide and not silver chloride. Okay? So it needs to be greater than 3.9 times 10 negative 11, and it needs to be less than 8 times 10 to the negative 9 molar. So it has to fall within that area. Okay. So if you're trying to get the bromine away from the chlorine, you could add the silver at a lower concentration, pull out the silver bromide, and then you could add copper to it, perhaps, purify away the silver, and you'd have copper bromide. Okay, so this is basically two examples in one.
Alright, sorry. You were explaining everything, I was writing. So you figured out the concentration of Ag for AgBr, concentration of Ag for AgCl, and then you only want AgBr, so you need to have higher than 3.9 times 10 to the negative 11, but not as high. Okay.
That's
So
right.
it needs to be in between.
It needs to be between those two amounts.
Because
Okay.
if you go higher than that one, then you'll get AgCl precipitate as well.
That's right.
Okay.
You'll get AgBr and AgCl precipitating at those concentrations, at that concentration. Okay, so we've talked about common ions like adding H plus to an acid, or increasing the concentration of a conjugate base in a solution shifts the equilibrium. Okay, so the presence of common ions decreases the solubility of salts. That's what we're going to see here. What is the molar solubility of silver bromide in a pure water and in a 0.0010 molar sodium bromide? Okay, so here we have silver bromide. The KSP is 7.7 times 10 negative 13. So S squared equals the KSP here. Okay. So if we can easily find S by taking the square root of the KSP, which is given to us, and we find S, the molar solubility, is 8.8 times 10 to the negative 7 for silver bromide. That's the solubility of it. Okay. For sodium bromide, here, okay. So this is our equilibrium equation for silver bromide, right? And here, if sodium bromide is going to dissociate, it's 100% dissociation. There's no really, we're not really creating that equilibrium. We're not creating that KSP necessarily. Okay, so it's going to dissociate 100%, and it's going to deliver 0.0010 molar bromine into the solution. Okay, what happens if I increase the concentration of this? It pushes it this way, right? So that's the Chatelet's principles at work, right? Increase the concentration of something, it moves away. Well, what is that doing? It's creating more solid here. So if I'm increasing only one of these things, then it's pushing it back this way, and it's pulling more and more silver out, okay, and causing it to become kind of decreasing the silver concentration while this one was increasing. So I'm pushing it all one way. We did something similar just yesterday, or not, was it yesterday? No, the day before, when we did our calculations of our K. We had a bunch of iron, or no, we had a little bit of iron and a ton of the other, the thiocyanate, and it pushed it all into that iron thiocyanate situation. And so we could determine the concentration of the iron thiocyanate from the concentration of the iron. Okay, so it's kind of the same idea. We're trying to force it one way. So by increasing the concentration of the bromine, we're pushing it this way. So the presence of this common ion is decreasing the solubility of the salt overall. Okay. So bromine 0.001 plus S is approximately 0.001 because S is so small. And so my KSP here is equal to 0.001 because we dropped that plus S times S, which is the silver. Okay. And S is now 7.7 times 10 to the negative 10. So it was 8.8 times 10 to the negative 7, but when you added the bromine, it caused that shift to be 7.7 times 10 to the negative 10. So it is now less soluble because of that presence of that common ion. It became less soluble. So essentially, you're just adding this to the S of the bromine, which makes it approximately 0.001. Drop that plus S. So 0.001 times S equals 7.7 times 10 to the negative 10. Okay, so the pH can change solubility because of the presence of a reaction that may be occurring. Okay, insoluble bases dissolve in acid solutions. So we just saw a calcium hydroxide solution. It was a fairly insoluble thing. We did this in the lab too, right? Well, some of you were successful at doing it, and then others of you didn't really do it that well. But you've added, it was a calcium hydroxide that you made, and it was a white precipitate. And then you filtered it, and you put some into into water, and it didn't dissolve really. But then, if you added acid, HCl, you took your hydrochloric acid and you added it. Okay, and insoluble bases dissolve in acid solutions. Then you were able to dissolve it. You were able to pull out that acid. Insoluble acids would dissolve in basic solutions because the hydroxides are reacting with the acids and forcing the the solution to become more and more soluble, okay? Because you're pulling out one of the, if you're pulling this out, this will shift this way. And so it will dissolve into solution, okay? So here for magnesium hydroxide, the KSP is 1.2 times 10 negative 11, so it's very insoluble. Here's my KSP, it's 4s cubed, okay, so I can solve for s, and s will equal 1.4 times 10 to the negative 4. This is my molar solubility. Hydroxide, the concentration of hydroxide is equal to 2 times s, so the concentration of hydroxide would be 2.8 times 10 negative 4 molar in solution, okay, of, as this thing is dissolving, which it doesn't very well dissolve, okay. pOH is 3.55, pH is 10.45 for the hydroxide. So if I know the hydroxide concentration, I can determine the pH and the pOH from that. That's all that's saying, okay. So here, let's just get to this, okay. If I lower the OH minus ion concentration, it will force this way. And how do I do that? By reacting it with H plus to form water, and that increases the solubility of magnesium hydroxide. So at pH is greater than 10.5, it raises OH, which would force it backwards, but decrease the solubility, okay? So if I increase the OH minus, obviously you would push it that way. But if I decrease it, it pushes it this way, okay? Okay. So this is kind of just going back to something we had done in one of the earlier slides where we're saying silver bromide, precipitate out the silver bromide before we precipitate out the silver chloride. So you can take different steps to do those sorts of isolations for different things. Okay, so in group 1, silver and mercury. Group 2, lead, bismuth, cadmium, copper, mercury. Okay. Here we start out with an HCl solution. It's going to precipitate out silver chloride, mercury chloride, lead chloride. And then here this becomes an H2S solution, which gives us bismuth sulfide. Okay, so you can see once you have them grouped here, you can precipitate them according to these different combinations of what you're adding or so forth. Okay. And isolate different compounds in a mixture of things if you needed to. All right. Not a big deal. You don't need to really know much about that. Okay, that's all we have for that chapter. So it's pretty basic. Determining the molar solubilities, find S. That's kind of hardest thing. So in your homework, you'll get a good idea of kind of what you really need to focus on. And it's a joint homework. It's like the end of 14 and 15 homework. Okay, because we don't cover a whole lot on this chapter. That's why it's such a. Okay, now we get into some more fun stuff. Okay, so we're going to move away from equilibrium now and talk about entropy and free energy and some more thermodynamic stuff, okay? So we want to understand energy and how it affects chemical reactions, because they are what drive chemical reactions forward. You have to absorb energy in order to break bonds. You have to release energy when you form bonds. And so we have to have that energy to drive our reactions forward. And some reactions are going to be spontaneous, like this guy. That's spontaneous, okay? Some reactions are going to be non-spontaneous, like this guy, okay? So we want to be able to describe reactions as spontaneous or non-spontaneous. And to do that, we're going to have to understand a few factors, okay? So here's some examples, of some spontaneous things. Water runs downhill. Sugar dissolves in coffee. At 1 atmosphere, water freezes at 0 degrees Celsius and ice melts above 0 degrees Celsius. Heat flows from hotter objects to colder objects. Gas expands in an evacuated bulb, meaning something that has no gas in it. If you put a gas in there, it will expand into that container. That's spontaneous. Iron exposed to oxygen and water reacts to form rust. Okay, that's a spontaneous process, albeit not a very fast rate of a spontaneous process, but it does happen spontaneously. Okay? Okay, so here's an example of that spontaneous process of the gas. If I have it in one bulb, and I open the valve in the middle, okay, then that gas will expand into both bulbs. And that is spontaneous. Can I do this? Can I do it that way? That would be a non-spontaneous process, right? That would require me to input energy into the system to force it backwards, right? So that is not going to happen. I'm not going to be able to force it back to the other side. Okay? Okay. Do you remember what enthalpy is? Okay, it's the heat energy. From when you guys did delta H, it's your delta H is the enthalpy, delta H. So does a decrease in enthalpy mean a reaction proceeds spontaneously? So what do I mean by a decrease in enthalpy? Delta H is what? Okay, negative exothermic. Okay, so here we have methane plus oxygen produces carbon dioxide and water. Delta H is equal to negative 890.4 kilojoules per mole. So we determined that because the formation of the products minus the formation of the reactants gives us a negative 890.4 kilojoules per mole. Okay. Here's another one. H plus OH minus forms water. Delta H is negative 56.2 kilojoules per mole. Okay. But here we have H2O solid to H2O liquid. Solid melting into a liquid gives us a delta H equal to 6.01 kilojoules per mole. So we have two of these reactions are exothermic, and one of them, well, here we got another one. Two of them are endothermic. Okay? So can we describe the process of spontaneity of a reaction simply by its enthalpy? Can we look at the enthalpy and say, this is spontaneous, it's exothermic. This is spontaneous, it's exothermic. But this is spontaneous and it's endothermic. So can I just say an exothermic reaction is spontaneous? All exothermic reactions are spontaneous. All endothermic reactions are non-spontaneous? I can't say that, right? Because that's not true. Now, for the most part, most exothermic reactions are spontaneous, and most endothermic reactions are non-spontaneous. Okay? But there are exceptions to that. So that means because there are exceptions, that there must be another factor. There must be something else that we have to consider in order to understand the process of spontaneity. And that's entropy. Entropy is the other factor. So, entropy is a measure of the randomness or disorder of a system. Now, measuring the heat of a system, that's a very simple process. Okay? How do I do it? I use a thermometer. I put a thermometer in my solution and I measure the temperature change. And I can describe the delta H of the reaction in the laboratory. But when I look at the randomness or disorder of a system, that is not necessarily a very easy thing to describe. Okay? So you can kind of look at it and identify whether the delta S is increasing or decreasing, meaning that whether the order or disorder is increasing or decreasing. But actually calculating the amount of disorder versus the amount of order, okay, is an entirely different process. Okay, so if my order is increasing, then I describe that as a negative. If it's a decrease in the disorder, I don't like to think of it as order. I like to think of it as an order. Okay, order. If my order is increasing, if my disorder is increasing, my delta S is positive. An increase in the disorder is a positive delta S. A decrease in the disorder is a negative delta S. So, if I go into your apartment, is that delta S going to be positive or negative?
Mine is going to my house right now. Delta S is sky high.
Delta S is sky high. Okay. So my kid's bedroom, same way, right? I walk in and it's just like the entropy in there is just off the charts sometimes. And so I can't even imagine how they can survive in that place, but they like it that way. So for it to get that way, does it require a whole lot of work? No. Because guess what? Delta S positive is spontaneous. That is a spontaneous thing. The order tends towards disorder spontaneously, requiring nothing, no energy. If you just sit in your apartment and you never input any energy to clean up, then the delta S is just going to increase and increase and increase and increase. Because what does it require to go the other way? You have to clean up. You have to get busy. You have to work. Okay? So this is the argument my kids use. Dad, this is spontaneous delta S process. They don't actually use that, but if they would, they could maybe get away with something, but they don't. They haven't figured that one out yet. Okay? So, but that's a process of spontaneity. Okay? A delta S positive is spontaneous. All right? And a delta S negative is non-spontaneous. So this is going to help us describe endothermic and exothermic reactions as whether they are spontaneous or not. Okay? When we consider the entropy as well. So like I said, calculating these entropies, I can easily describe whether it's positive or negative. Like I walk into a house and I describe whether it's positive or negative. But actually calculating the amount of entropy, the amount of energy associated with the entropy of that system is a whole different ballgame. Okay? And it has to do with these microstates. So here I have 1, 2, 3, let's say, molecules of gas. 1, 2, 3, 4 molecules of gas. Okay? And they can distribute themselves in the first situation into one of the two boxes. In the second situation, they can distribute themselves in this manner. Okay? In the next situation, they can distribute themselves in that manner. So this is a very simple example because there's only 4 molecules of gas here. You don't usually have 4 molecules of gas. You usually have mole amounts. 6.022 times 10 to the 23rd molecules of gas. And imagine the number of microstates that you would have with that amount of molecules of gas. Okay? So this is something that you luckily do not have to calculate, okay, using the microstates, which is W, the number of microstates, okay. But then if you did know W, the number of microstates, you took the natural log of that times another K, you could find the change in the delta S, okay. But if you are given the delta S of formation, then that's a whole different thing, because you can calculate the delta S of the reaction from the delta S of formation the same way you did it from delta H products minus reactants. It would be delta S is products minus reactants as well, okay, as long as you know what the delta S is of this reaction. Okay, so here our solid is liquefying. Is that an increase or decrease in the entropy? Increase. That's an increase in the entropy, right? That's what it wants to do. That is a increase in the entropy, and those molecules want to spontaneously fall apart. Liquid to vapor, same thing. Here we have the solute dissolving into the solvent. What is it? Delta S positive, delta S negative. How do I describe it? So the solute is dissolving. That's a positive delta S. It's becoming more disordered. But look at the solvent. Would you describe this situation or this situation more ordered? So this has become homogeneous. This is heterogeneous, right? So you could almost say for the solvent, it has become more ordered. For the solute, it has become more disordered. So you might want to take into consideration both of those when you're trying to describe that process, okay, for that. Okay, here's a system at T1, and here's a system at T2. T2 is greater than T1, okay? So this is going to absorb energy. It will absorb energy from something else that the higher heat will move to it spontaneously and cause the increase of the temperature here, okay? Okay, bromine liquid to bromine gas. If it says delta S is less than 0, what does that mean? Liquid to gas. I'm sorry, greater than 0. Did I say? I was saying it's greater than 0. That's a positive delta S, right? Liquid to gas, positive delta S. Here we have a solid to a gas, so this is sublimation, also a positive delta S situation. Okay. How does the entropy of a system change for each of the following processes? Okay, let's just get them up. Okay. Condensing water vapor. How would I describe the delta S? Negative. Okay. because it's going from gas to liquid. So that would be a negative delta S process. Randomness decreases, delta S is less than 0. Okay? Forming sucrose crystals from a supersaturated solution. So basically from something dissolved and it precipitates out. What did you say earlier when the solid dissolved? Okay, so what about the other way? Okay, so we would describe it in the other way. The randomness is decreasing. All right. Heating hydrogen gas from 60 to 80 degrees Celsius. Increase randomness, because the energy of the system, you're adding energy, those molecules are going to start moving faster and faster.
Start running around.
That's right. Okay, the energy increases. The entropy increases, excuse me. So the randomness and the disorder is increasing. Subliming dry ice. What does that mean? Solid to gas, sublimation. It does. Randomness is increasing. Okay? So our delta S is greater than 0. Okay. So entropy is a state function. State functions are properties that are determined by the state of the system regardless of how the condition was achieved. Which means final minus initial. The path doesn't matter. Okay? That's what they're saying. The path that you take to get there doesn't matter. Look at these two hikers. This one goes from here up and reaches the top. Final minus initial, and I can describe the change in the entropy. This guy goes like this. Final minus initial, and I describe the entropy. Both of them have the same entropy. Okay? No, it doesn't.
No, I mean like that puts in more work to get to the spot he's at. But you're talking about elevation.
No, I think.
No, it doesn't. It doesn't take
Blue-
more work.
So blue put in more energy for a shorter period of time. That guy put in less energy for a longer.
They
period
put in
of
the
time.
exact same amount of energy. So if I let me see if you guys get this, okay? So if I want to take the lug nut off of my tire, okay, and I have a ratchet like this long, and I'm trying to do that, it's going to require a lot of energy, right, to do that. But if I have a lug nut and I take a pull that's like this long, I feel like it takes less energy, right? It doesn't. It doesn't take less energy. It takes the exact same amount of energy. It's just here, okay, I move it farther. There's more energy, so it moves it farther. But all of that, it only moves it a short distance. So I'm using the same energy for the same amount of twisting. Okay?
Someone said they don't know what the lug nut is.
Okay. Okay. So, state functions describing changes, okay, are energy, enthalpy, pressure, volume, temperature, and entropy. These are all state functions. Final minus initial, final minus initial, final minus initial, right? That's how we always describe all of these. Final minus delta, enthalpy, delta H, okay? Temperature, delta T. Entropy, delta S, okay? So final minus initial. That's how we describe these state functions. So luckily for you, if you go to the back of your chapter in your book, or of any chemistry textbook. Okay? Then there will be like 4 pages of thermodynamic data. And it'll be like delta H this, delta S this, delta G this, okay? And you'll have all that data right there to tell you the delta H's and the delta S's and the delta G's that you can use to determine something else, okay? So there's all that data in the back of your books. It's charts of data, okay, like this one. Water, the standard entropy value for water is 69.9 joules per Kelvin mole. Okay? For water liquid. Water gas, it's 188.7 joules per Kelvin mole. Does that seem right? Is the randomness or disorder greater here or here? For the gas. Okay, that seems right. The randomness has increased for the gas, so in the gaseous phase, at 25 degrees Celsius, okay? Wait, does that make sense that you would have water in the gas phase at 25 degrees Celsius? Nope.
Damn, I was right. I was with you on that one.
Oh my goodness.
It makes sense.
If this is water and I put a lid on it at 25 degrees Celsius, what's going to be right here? There's going to be a water vapor pressure, right? There's going to be a water vapor pressure in what phase? Gas phase. So do I have gas at 25 degrees Celsius for water? Sure do. Okay? And its randomness and disorder is 188.7 joules per Kelvin mole. Whereas in the liquid phase, it is 69.9 joules per Kelvin mole. What if I increase the temperature of this water, or of this gas? Would that change my this? Yeah, it would be more random, right? It would be even more random. They'd be moving faster and more random. Okay, that would increase the entropy, the entropy of this. Okay, so the first law of thermodynamics is that energy cannot be created from one form to another. This is delta H, okay? The first law of thermodynamics is the enthalpy, delta H, okay? The second law of thermodynamics, delta S, is that the entropy of the universe increases in a spontaneous process and is unchanged in equilibrium. Okay, so energy cannot be created or destroyed, right? You can't. I don't create energy. It just gets transferred. If I eat a salad, the energy from the plants is being transferred to me. That's where I'm getting some energy, right? But I didn't create that energy. The plant didn't create the energy. Where did the energy come from for the plant? From the sun. Did the sun create the energy? Nope. It didn't create the energy. What did it do? It released it. Where is the energy stored? In the hydrogen molecules of the sun. So through fusion, when those hydrogen molecules fuse together, it releases, I can't even describe the amount of energy it releases. It's just like insane amounts of energy that it releases, okay, through fusion. So it releases all that energy, and it travels here to our planet, and our plants absorb it, right? And then we eat the plant, so that energy is getting transferred from the sun to the plant to us because of that fusion process, okay? And so eventually, the sun could actually burn out. Do suns ever burn out? Mm-hmm. Because there's no more hydrogen, right? They burn out, there's no more hydrogen, excuse me, or they could become too dense, maybe, and explode. So that's the other option. And you could create a black hole. That's fun. Okay. So we will never be around when that'll happen to our sun. That's like, yes. So we don't have to. We're not too worried about that for us, but maybe our future generations might be more concerned about it. Okay, but that energy was not created by the sun. It was only released. Those hydrogen molecules all have that energy stored within them. They're just releasing it. Nuclear energy releases undescribable amounts of energy. Okay? Just crazy. I mean, when we're looking at molecules that react based on their valence electrons, right? We create covalent bonds from valence electrons. We release energy, or we absorb energy in kilojoules per mole, 50 kilojoules per mole, 100 kilojoules per mole. Okay? That pales in the face of the amounts of energy released during nuclear reactions, from nuclear reactions. And if we could ever figure out how to harness that energy in a safe way, it would be a lot more beneficial to us. But that's a hard thing to do. Okay, especially for fusion. So for fission, they just kind of do that in these nuclear reactors, whatever, that sometimes get busted open and contaminate everything. But for fusion, they haven't really found a good way to, like what our sun does, they haven't found a good way to contain that energy in a safe process. Okay, so standard entropy of a reaction, the delta S of a reaction. So it's the same as you've seen before for the delta H of a reaction. Products minus reactants, right? So if you go to the table and get the data for C, for D, you add those together, and then you do products minus the sum of A and B, right? Multiplied by their coefficients, everything. So just the same way you did it for delta H in Chem 1. And this is the type of reaction, or how it's written. Okay? And I think somebody at the beginning of the semester saw this. They're like, let's skip that reaction, that equation. It's not that complicated, okay? It's just like the sum of the delta S for the products minus the sum of the delta S for the reactants. Products minus reactants. It's one of the easiest equations you'll have, okay? What is the standard entropy change for the following reaction at 25 degrees Celsius? Okay, S, CO, S for O2, S for CO2. So here we get this table from the back of our book, or they give it to us in the question. This is our balanced chemical reaction, which we need. So for carbon monoxide, we have 2, so we have to multiply 2 times the entropy of carbon monoxide plus the entropy of the oxygen.
This one's times 2, not squared.
Oh, yes, this is just times 2. Because we're just describing, this isn't equilibrium, okay? It's just products, carbon dioxide, times 2. Because this right here, the data from the table gives it to you for 1 carbon dioxide. You need to describe it in this reaction for 2 carbon dioxides. So 2 carbon dioxides, so 213.6 times 2. That's going to go here. minus 2 times that of carbon monoxide, which is 197.9, plus 205.0 for this term. Okay, and then it's products minus the reactants. Okay, let that disappear. Okay, so the delta S of this reaction equals 427.2, which is carbon dioxide times 2, minus 395.8, which is carbon monoxide times 2, plus 205. Okay, and that gives me negative 173.6 joules per Kelvin times mole. Is the entropy increasing or decreasing? Delta S, negative. Decreasing. Okay, is that what you would presume here? 2 gases to 1 gas? Is that a decrease in entropy? Yeah, right? So from 3 moles of a gas to 2 moles of a gas, we have a decrease in the entropy. That's what we would assume would happen. And it is. Okay, and this is kind of what, if a gas produces more gas than it consumes, delta S is going to be greater than 0. If the total number of gas molecules diminishes, then it will be less than 0. If there is no net change in the total number of gas molecules, then delta S may be positive or negative, but delta S will be a small number. Okay? If it's like close to the same amount on both sides. Okay, what is the sign of entropy change for the following reaction? Solid plus a gas into a solid, just a solid. Decrease in the entropy because we went from a solid and a gas to no gas, just a solid, right? So that's going to be a decrease in the entropy. Yep. That's what we'll do. Okay. So we can describe entropy, obviously, for the system and for the surroundings, just like your enthalpy. We describe it for the system and the surroundings because if your entropy, if your enthalpy is decreasing for the surroundings, it's increasing for the system, and vice versa. Okay. So here we see that process again, surroundings to the systems. Here the heat is being released from the system to the surroundings. So the system, the delta S for the surroundings would be greater than 0. It would be increasing. Okay. Now when we talk about delta S being positive or negative, one thing you have to understand is that a negative delta S doesn't actually mean a negative delta S. It just means a decrease in the entropy. It's just describing it. Because to reach an actual negative delta S would be impossible. Because to do that, you would have to go below the coldest temperature, which is what?
0 degrees Kelvin.
0 Kelvin. So you would have to go below 0 Kelvin to reach a negative entropy, meaning that that the state has become more ordered than possible. Because at 0 is the greatest possible order of your system. Because all energy is extracted from the system. Everything's in its situated state, in its solid state, and as organized as it can be. Okay? So it's a description, not a real actual negative delta S. Okay? It's describing the entropy as being positive or negative. Okay? Okay, oh, and that's just kind of what we're just getting to, right? The entropy of a perfect crystalline substance is 0 at the absolute 0 temperature. Okay? So absolute 0 is something that scientists are trying very hard to actually accomplish. And it's a very complicated process to get anything to absolute 0, meaning that there's no more motion in a molecule. Because at any temperature, there will be energy in a molecule, and that molecule will be vibrating, if nothing else, at least vibrating. So to remove all energy from it would cause it to stop vibrating and be in its most perfect state. Okay? And that would be at absolute 0, or 0 Kelvin. Okay, which is this third law, that a perfect crystalline substance is at absolute 0. Okay, there are no more. There's only one state, one microstate that molecule can be in. Okay, and S is equal to 0. Okay. So we've described delta H, and now we've described delta S. And those two things together will describe the spontaneity of a reaction through delta G. Delta G is Gibbs free energy. Okay? So here we have a spontaneous process for delta S, and at equilibrium process for the system and the surroundings will equal 0, because whatever is the change in delta S one way is the exact opposite of the change of delta S in the other way. And so that's equal to 0 for the surroundings in the system of the universe. Okay? So for a constant temperature, constant pressure process, okay, delta G, which is Gibbs free energy, equals the change in the enthalpy minus the change, minus the temperature times the change in the entropy of the system. So this is describing the delta G of the system here, okay, which is Gibbs free energy. So if your delta G is greater than 0, the reaction is spontaneous. If delta G is greater than 0, and depending on how you have the reaction written, so whatever is the forward direction in that reaction, if your delta G is 0 for that forward reaction, then it would be, if the delta G is negative in the forward direction, then in the reverse direction it would be positive, okay? So we're describing it in the forward direction. The reaction is spontaneous in the forward direction if delta G is negative, okay? So delta G less than 0 is negative. This is a spontaneous reaction. If delta G is greater than 0 or positive, the reaction is non-spontaneous. Okay? It is non-spontaneous in the forward direction, but it is spontaneous in the reverse direction. Okay? So essentially, if your reaction is spontaneous one way, it will be non-spontaneous going the other way. All right? So delta G equal to 0. The reaction is at equilibrium. Okay? It's between spontaneous and non-spontaneous. It's right there in the in-between at 0. Okay? Just a slight change in the temperature will cause it to go one way or the other when it's at equilibrium like that. Okay? Okay, the standard free energy of a reaction, delta G, is the free energy change of a reaction when it occurs under standard state conditions. So remember, standard state conditions are the delta H's, delta S's for these reactions. So once again, we have products minus reactants. This should be a very familiar equation now. It's exactly the same equation you use to find delta H and delta S. It's the exact same one. Products minus reactants. They give me the delta G of formation from my chart in the back of my book. And I can take the delta G of formation for C plus the delta G of formation for D, add them together, and I subtract those from the delta G of formation of A plus the delta G of formation for B. Okay? So this is not a new equation. Products minus reactants. These are state functions, final minus initial, right? So that's what we're getting to here. So once again, and this will be the equations that you're given on your reference material. Okay? So just understand what that means. Products minus reactants. The sum of the products minus the sum of the reactants. Okay? And your delta G is the energy change that occurs when 1 mole is formed from its elements in their standard states. So the delta G of formation is the energy change when you're considering both delta H, which is energy, and delta S, which has energy associated with it also. Okay? So those two things combined, when I consider those two energy equations, I can calculate the free energy from those two things combined. Okay? And that's my delta G, my change of energy of this reaction. The free energy that is released for this reaction. Okay? And it is either positive or negative, and it describes spontaneity. So if it's negative, delta G negative, it is a spontaneous process. If delta G is positive, it is a non-spontaneous process. Okay, so if you have the delta G of formation for any element would be 0. So if it's O2 or N2 or magnesium solid, etc., in its elemental state, it would have a delta G of 0. So they wouldn't necessarily need to give you that, just like when you calculated delta H's. Okay? Just the same as when you calculated a delta H. Remember, for delta S, that's not the same thing. Okay? It's not the same idea. Okay. We don't really need to. So here's some standard states. For a gas would be 1 atmosphere. Liquid would be the pure liquid. Solid would be the pure solid. Elements, their delta G's would be equal to 0. Okay? And we're going to have these at 1 molar concentrations. That's how we describe these things, okay, in those states. What is the standard free energy change for the following reaction at 25 degrees Celsius? Okay, we're going to use products minus reactants. We find the delta G of formations from our book, okay, and here we're going to multiply the carbon dioxide by 12, the water by 6, the benzene by 2, okay? And oxygen, why don't we have an oxygen over here times 15? What was that? Good, and so its delta G is 0. So we don't include it. Okay. Why is O2 0? Because it's in its elemental state. Okay? So anything in its elemental state will have a delta G of 0, so we don't have to include it. Okay? You guys did the same thing for delta H's. If you're trying to find the delta H of a reaction for any element, the delta H of a reaction was at 0. I mean, I'm making the assumption that that's what you guys did. But you should have done that in Chem 1, where you found for thermodynamics, delta H, products minus reactants, and these were at 0 for their elemental state. Okay? So then we put our numbers in. You would find these from the back of the book. Let me see. Let me see if I can actually find it. I'll do it. do it later. Okay, but you would look it up in the back of your book, and you would find this data from the table. You can plug those numbers in for the delta G of formations for these different compounds, and then you would multiply them by their coefficients. Okay, add them together, and then subtract products minus reactants. Okay, products minus reactants. Is this reaction spontaneous at 25 degrees Celsius? Yes, it is.
Yes.
Because it's delta G negative. Delta G negative means spontaneous reaction. If it was a delta G positive, it would be a non-spontaneous reaction. Okay? But this is releasing energy, right? It's releasing energy. The Gibbs free energy is being released in this reaction, whereas in a non-spontaneous process, it's requiring that energy, okay, for it to proceed forward. It requires the energy. Okay, so this is the equation. You'll be given this equation on your reference material, delta G equals delta H minus T delta S. We're actually going to do a lab, too, where you're going to use this equation to determine delta S of a reaction, okay, from this equation. You're going to use this equation, rearrange it. You can see, well, I'll explain it later, but essentially you have to set delta G equal to 0, and that makes this whole equation become a little simpler. But we'll look at that later, okay? All right, so this is kind of how we can predict what the sign of delta G will be from the sign of delta H and delta S. No numbers, just their sign, okay? So if delta H is positive and delta S is positive, endothermic with an increase in the entropy or the disorder, okay? So both of these are positive. This reaction proceeds spontaneously at high temperatures. At low temperatures, the reaction is spontaneous in the reverse direction. Okay? So if this is positive and this is positive, okay, then because this is a negative, it changes this to a what? Kind of just changes it to a negative, right? So positive plus a negative, okay, then if this term becomes greater than this term, then it becomes delta G negative. But if this term right here is greater than this one, then it remains delta G positive. So what changes whether it is spontaneous or not? No, the delta H is going to be, the delta H and the delta S are constant. What changes it? Temperature. The temperature is what will determine whether this reaction will become spontaneous or not. Okay? So increases in the temperature will change this whole term right here, or decreases in the temperature will change that term, and then it will overcome the delta H or not, okay? And then your delta G will remain positive or it will become negative. So, if the signs are the same, it is temperature dependent, okay? Well, what if the signs are opposite? Plus, minus. Now what happens? Now it becomes plus plus a plus, okay? Can I ever make it negative? I can't. I can never. Doesn't matter what the temperature is. Doesn't matter at all. I can never make it anything but a positive delta G. It's the only thing I can make it is a positive delta G, right? Okay. So that's for that situation. What about for minus plus? It becomes minus plus a negative. Can I ever make it anything but negative? I can never make it anything but negative. So delta G is negative. So if it's a negative and a positive, it will always be delta G negative. Okay? Delta G is always positive. Delta G is always negative. So it's always non-spontaneous in this one, and it's always spontaneous in this one. Okay? Negative, negative. Negative minus a negative, or plus a plus. So this term, that positive term, can overcome the negative one, right? And it could force this delta G to become positive, okay, if the temperature allows it to. So the reaction proceeds spontaneously at low temperatures, but if I increase the temperature, that's going to cause that delta S to become, that term to become more and more positive, and it will overcome it and become non-spontaneous at higher temperatures. All right? Okay. So that's how I'm going to describe delta G simply from the signs. And you'll have questions like that. What is the sign of delta G? What is the sign of delta G given that delta H is positive and delta S is positive? It's temperature dependent. What is the sign in delta G? Or it's temperature dependent. It's spontaneous at high temperatures, and it's non-spontaneous at low temperatures. It's spontaneous at high temperatures, so positive plus a negative. Okay? So if I increase the temperature of this situation, what happens? The delta S term becomes more and more negative, right? And so at high temperatures, it becomes spontaneous. It becomes negative. But at low temperatures, it remains positive. Okay? So the other situation is where it was negative minus a negative, negative plus a plus. So in that situation, it's exactly opposite. Okay? At high temperatures, it becomes more and more positive. It will become non-spontaneous. At low temperatures, it becomes less positive, so it'll remain negative, and delta G will be spontaneous at low temperatures. Here it's spontaneous at high temperatures. Okay? So you might need to describe them in that way. So try to understand kind of the concept behind this.
Temperature's always in Kelvin here.
It's in Kelvin?
That's why you can't have a negative.
That's absolutely true.
I was about to say, what if you have a negative temperature, but never mind.
Okay, good. It's in Kelvin. Yeah, you're right. You won't have any negative temperatures here. Okay, so this will be a very, this is very straightforward then. Okay. So here we see if delta H is 177.8 and delta S is 160.5. Okay. Then delta G equals delta H minus T delta S. Delta G naught at the standard state these standard states at 25 degrees Celsius becomes 130.0 kilojoules per mole. Okay, so we have a delta H positive, a delta S positive, right? Delta H positive, delta S positive. Okay? So where does delta G become 0? Well, if we solved for the temperature and put delta G equal to 0, we could see that it would be 835 degrees Celsius. So delta G 0 equals delta H minus T delta S, and I solve for the temperature when it's 0, and it would allow me to determine that temperature. Okay, 800. Oh, well, this is a. It would be. You'd have to put it. You'd find it in Kelvin, because these are in joules. And by the way, one thing I really want to emphasize. Look at the units here and here. This is the biggest mistake that everybody makes. They try to use these terms just like they are here. Delta H's are in kilojoules per mole. Delta S's are in joules. That doesn't work. Okay? That doesn't work. You have to have them in the same units in order to use them. So you got to convert one or the other. So you could convert your delta H to joules, and then you would be able to use it. Okay? And then you're going to find a Kelvin temperature, and here that you're going to have to put it back to Celsius, and then that would describe what's happening here. Okay? These are, if I go right above 0, okay, then my reaction becomes spontaneous. Okay? At those temperatures, because delta G0 is at that equilibrium, and if I just bump it up above it, boom, it becomes spontaneous. Now it's a spontaneous reaction. Okay, so setting delta G equal to 0 does help us a lot of times, like in a situation here. Like I said, in the laboratory, we're going to do a situation like this. Okay, so delta G at 0 means it's at equilibrium. Okay, so for example here, H2O liquid to H2O gas. Okay, by setting delta G equal to 0, we can eliminate the delta G term, and we could solve for delta S. So let's just see how that is. 0 equals delta H minus T delta S, right? So I can minus delta H minus T delta S, and then I could, equals negative T delta S, delta H over T, because I bring both negative terms over to the same size, it makes it a positive, equals delta S. Okay, and so now I can solve for my delta S from the delta H and the temperature that I have. Okay, so in this case, delta H is 40.79 kilojoules per mole. The temperature is 373 Kelvin, and I'm able to find my delta S. Okay, and you'll see it's in kilojoules per mole, but you're going to have to convert it to joules because that's how you described the entropy is in joules, not kilojoules. Okay, let's see. We don't need to belabor that. Okay, this is another important equation that you need to be familiar with. The delta G of a reaction is equal to the delta G naught at standard state conditions. Delta G naughts are at 25 degrees Celsius, standard state 1 molar conditions, plus R. Which R do you think you're going to use here? Yeah, 8.314, because that's the energy R, right? And we're talking about energy, so we're going to use our energy R, not our liter atmosphere Kelvin mole R, okay, which is the gas constant. We're going to use the 8.314 joule R here, times the temperature, times the natural log of Q. What's Q? Reaction quotient. Okay, so here we're bringing equilibrium back into this a little bit. Okay, Q equals products over the reactants, right? If you know the initial concentrations of everything, you can calculate Q. You take the natural log of that times RT times the delta G of formation at its standard state conditions. Why isn't that erasing? And you will get a delta G. Okay, for that reaction. Okay, R is the gas constant, T is absolute temperature, Q is the reaction quotient. You guys knew all that. Good job. At equilibrium. Okay. Delta G is equal to 0 at equilibrium. Okay. And Q equals K. So here we've kind of simplified it, right? Because we said delta G was 0. So this delta G naught, now you can find the delta G at the standard state conditions if you know RT, L, and K, because the reaction quotient at equilibrium is equal to K. Okay? So if it's not at equilibrium, you would do this. If it is at equilibrium, you would use this because K is your equilibrium constant. And then you just need your equilibrium constant. You either know it or you calculate it, products over reactants, okay? If they give you the equilibrium concentrations, not the initial concentrations, and then you can find it. Your delta G naught is equal to negative RT times ln of K. Okay. Okay, so from that equation, if K is greater than 1, natural log of K is positive, okay? Delta G will be negative. If the natural log of K is negative, then your delta G will be positive. Okay? So in this case, you would be able to describe the reaction as either to the right or to the left in equilibrium. To the right or to the left. Reactants, products are favored over reactants, okay? Because this is less than 1, this is greater than 1, so reactants are favored over products at equilibrium, okay? And that's how, so delta G negative or positive would also tell you essentially which way the reaction is favored, okay? Just like a K would tell you which way they are favored. Okay, so reactions a lot of times can be coupled to other reactions, and this happens most often in our bodies because there's this molecule in our body called adenosine triphosphate that carries out most reactions. Most of the reactions need you to add energy to them for them to occur. They're non-spontaneous reactions. They need this energy. And how are they going to get that energy? Well, the molecule that they do it through is through this ATP molecule. So ATP is produced, right, from glucose. So glucose is broken down, and the glucose, as it gets broken down, produces carbon dioxide, and through that process in the Krebs cycle of as it cycles through, it's producing things like FADH and NADH plus, and those things are getting taken to the electron transport chain, and in the electron transport chain, hydrogens are building up in the membrane interspace of the membrane of the mitochondria, and electrons are getting passed like on a wire, basically. Okay, something is sucking basically electrons towards it. And what is that thing? It's oxygen, right? And those oxygen molecules that we breathe are sucking those electrons towards it through the electron transport chain. And they accept those electrons, and you're going to form water in the end, because the hydrogens are coming through the ATPase. It's amazing, that ATPase. It's like a motor. It's a motor. It turns, and that motor is slapping phosphates onto ADP, right? And as it turns, those hydrogen, that pressure of the hydrogens is pushing that motor. Just like if you were blowing through something and it was turning it, the hydrogens are pushing that motor. And as they're coming down, the oxygens are getting reduced by the electrons. And then those hydrogens and oxygens come together and they form water. And the ATPs get slapped onto the ADPs. Or sorry, the phosphates get slapped onto the ADPs. and you produce ATP. Okay, that's a simple process, right? Okay. So that's what glucose has to go through this gigantic, enormous process in order to become ATP. So glycolysis and Krebs cycle, electron transport chain, like all this stuff, right? And it's just a big process to slap a phosphate onto that ADP. But why do we need to do that? Because when I create an adenosine triphosphate, okay, so we have, I'm probably going to draw this wrong. Okay, you have these adenosine molecules, and they have 3 phosphates. And do you know how hard it is to stick that 3rd phosphate on there? It's tough. It's tough to stick that 3rd phosphate on there. And so when it's stuck on there, that last phosphate, it's storing all this energy in the bond, and it's just barely holding on. And so then I go and I couple that ATP reaction to something else. The reaction of the phosphate coming off, I couple it to something else, and as that phosphate comes off, okay, and gets added to something else, you add the phosphate to something, you pull it off of ATP, and you add that phosphate to something else, and what happens when you create bonds? That energy is released, okay? And so you're coupling that energy to something else. And as you do that, it drives the reaction of whatever you're trying to do. So let me see. I think they actually use a bad example here. They do use a bad example. Okay. So this is a non-spontaneous process, right? K is greater than 1. Alanine to glycine is a non-spontaneous process, but you couple it to the ATP, okay? And then you get ATP plus water plus alanine plus glycine. And now your free energy is spontaneous because I coupled this process of the ATP here getting added to this. I coupled it, and it drives that process forward with free energy. Now it's spontaneous. Now it's a spontaneous process, okay? Because it's allowing energy to be released. Okay, we don't need to focus on that. Oh, there it is. It wasn't far off. I just forgot my sugar. Okay. So that's right. You got to have a base, sugar base, right? The sugar backbone of because it's a nucleotide, and that nucleotide is in DNA. Okay. How could I forget that? Okay, so here we see, well, I don't know if we really need to talk about that. All right, that's good. All right, so we'll do some examples of this next time. Okay, of some of the math in that chapter.